Hey everybody, welcome back to the titration video series. In part A, we went over what the titration was, the technique, and I provided you with the link to actually see the procedure, so hopefully you were able to do that. The focus of this video will be an analysis, or just an example problem of how you would use the data you collect to actually determine the solution's concentration. So a quick review of some terms, and again, we'll just set up our document to go. So the titration is a procedure used in the lab for chemical analysis. Remember, it has 2 points: to determine an unknown concentration or to track changes in pH over time. Right, so the purpose of those depends on the scenario that they're being applied to, and I talked about a few in part A. So the standard solution is what has a known concentration. So that we choose that solution. Right? We know its concentration, and we choose it because we know its concentration. In the end, we'll be using that under the assumption that the moles of acid are equal to the moles of base. So as long as we know one of them, we'll be okay. Now, that helps us to reach what's called the endpoint. The endpoint is going to help us to identify what the equivalence point is. So you can see that that's our first term. This is when the moles of acid equal the moles of base, and we said specifically the moles of hydrogen are equal to the moles of hydroxide. So because we can't see that and it's theoretical, the endpoint is when the indicator changes color change of the indicator for a brief amount of time, but not too quick, and it tells us to stop the neutralization process, that we're done. Even though they're not the same, it's a negligible difference. So if we can time a reaction to stop at the color change, which takes a few trials in most cases, and we had said 3, right? The difference between the two will give us an acceptable error range. The equivalence point happens at a specific pH. Sometimes it's 7, sometimes it's not, as you'll see in parts C and D of the videos. And we choose an indicator that changes colors at this pH change. So in most cases, if the pH changes at 7, we choose a specific indicator than if it doesn't. So from a calculation standpoint, we know that in our scenario, in general, the number of moles of a solution is equal to the concentration times the volume of that solution. So you can see that there. At the endpoint, we say that the moles of hydrogen equal the moles of hydroxide. So based on that, and by substituting that in, the concentration of the we should say the hydrogen is equal to the volume of the hydrogen, and then the concentration of hydroxide times its volume. Right, now why we say that is because the hydrogen and the hydroxide represent the acid and the base. So you'll often see this abbreviated as CAVA equals CBVB, and it's all based on this statement here, that at the equivalence point, the moles of acid equal the moles of base, and we just substitute in measurable values for that. So that's a very useful equation. Now, that's all assuming that it's a 1-to-1 ratio. If it's not a 1-to-1 ratio, then we can do a couple more steps using mole ratios. So let's take this as an example. Phosphoric acid being titrated with sodium hydroxide. You can see that it's a ratio of 1 mole of acid for 3 moles of hydroxide. The reason for that is there is 3 hydrogen ions that need to react with bases. Right? So we need 3 times as many hydroxides in this case, of which there are only 1. So when we factor that in and we determine the concentration of the unknown, remember that we can write mole ratios to determine what the actual concentrations are. So in this case, it's a 1-to-3 ratio. The concentration we find will be a little bit different, and we'll use a specific example to determine that. The last step in all of this is, once we know the number of moles of the unknown solution, which we had said was the sample, we can calculate the unknown's concentration using the number of moles divided by the volume, and this equation up here will substitute in with that. So let's look at an example. A student in a laboratory adds 36 milliliters of standardized 0.66 moles per liter NaOH solution. So because we have a concentration for that, that makes it our titrant. So the titrant's a base. Then we're told that we used a 20 milliliter sample of sulfuric acid, excuse me. So let's draw a little diagram of this. Erlenmeyer flask holds our acid sample, which is sulfuric acid. We don't know its concentration, which is why it's the sample, but we know its volume is 20 milliliters. Then above that, we have the titrant, which in this case is the sodium hydroxide, because we know its concentration and we know its volume. Now remember what the volume represents. That's how much it took to get to the end point and cause a color change, which represents the equivalence point. So we can say at the equivalence point, based on above, the moles of hydrogen are equal to the moles of hydroxide. So we can say CAVA equals CBVB. That's the assumption of all titrations. So we have all of our numbers here. We can substitute this in. We don't know the concentration, but we know its volume. Right. And if you're wondering why I'm using milliliters, as long as volume is the same on both sides, the conversion would cancel out. So if you'd like to convert that to liters, it's okay. If not, because they're both in milliliters, they'll cancel out when we divide. So by calculating this, we get 0.66 times 36 divided by 20. So we find that the concentration of the acid is 1.2 moles per liter. Now, we have to be careful. This represents the concentration of the hydrogen ions. What we're being asked for is the concentration of sulfuric acid. And if we look at the formula for that, okay, the concentration of phosphoric acid, right, if it dissociates into its ion, contains 2 hydrogens and 1 sulfate ion. So because it's a 2-to-1 ratio, we should use a mole ratio to figure out how the concentration changes. So for every 2 moles of hydrogen, there is 1 mole of sulfuric acid. That ratio comes from the coefficients. So if we know that that concentration is 1.188, and we're trying to find that, if we isolate, we find out that it's half, or 0.594 moles per liter of sulfuric acid. And that is our unknown concentration of the sample. So we use the concentration of the hydrogen based on the color change of the indicator to determine the concentration of the substance. Now, I'll do another example with this here, and I'll do it a different way using stoichiometry so that we don't have to convert from acid to base. So what's the concentration of a solution of HCl? So because we don't know the concentration, that's our sample, neutralized by 48 milliliters of NaOH. So let's write a reaction for this. NaOH plus HCl, it's neutralization, so we form water and a salt. In this case, if OH and H combine to form water, NaCl will be the salt. So what we're telling ourselves is that the concentration of sodium hydroxide is 0.10. Its volume is 48.0 milliliters. We don't know the concentration of that, and its volume is 30 milliliters. So we can treat this like a stoichiometry problem, because that's essentially what it is. We just need to know when the color change happens to determine the volume of the titrant. Okay, so that's titrant and that's sample. And just one more time, we know that it's the titrant because we have its concentration. So this is a 1-to-1 ratio, right, when it's all balanced. So we know that for every 1 mole of sodium hydroxide, we have 1 mole of hydrochloric acid. So moles are equal to concentration times volume. Here we need to convert it to liters, however, because there's nothing to cancel out. So 0.1 times 0.048, and we've got 4.8 times 10 to the negative 3 moles. Now by knowing that, right, and this is more universal, we can determine the number of moles of HCl. Right, so the moles of HCl are 1-to-1. When we isolate, they'll be the same. Okay, that's back from our stoichiometry. And now we can say that its concentration is equal to moles divided by volume, which equals 0.0048. And its volume of the acid is 30 milliliters, so we'll say 0.030 liters, to get a value of 0.16 moles per liter. As you can see, we had that bolded already. So two different techniques, both give you the same result, and they're both understood to be the same process. Okay, so understand what the equivalence point is and how it represents an equal amount of hydrogen and hydroxide. And then depending on the mole ratio, be sure to take that into account. So you can try out that last example there, understanding that you'll get 0.45 and deciding between barium hydroxide and hydrochloric acid what the actual value is. So hopefully that helps clear it up. There's your two methods of using that volume. Okay, when we get the volume of the titrant, understand that it is after, and that's the average of 3 trials. Okay, so when we collect our data, we'll be sure to use those. Hopefully that helps, and good luck with the review questions that are attached. The homework for this would be the worksheet, questions 1, 2, 3, and 4.